Thanks everyone for being here. It's a great pleasure today to have Jon Epstein, who's a senior research scientist at the Center for Computational Mathematics at the Flatiron Institute in New York, which we all know very well. And today he's going to be telling us about degenerate diffusions in populations.
So thank you very much for this invitation. It's a fabulous place. I've never been here before. So I want to talk today about some work, an analytical work I did with Rafe Mazzeo, and the numerical work is really largely the work of Jon Wilkening, but I work with him to some extent. So I don't know how much people know about population genetics, so I'm going to start close to the beginning. So in population genetics, you study the distribution of variance in a reproducing population, and you study how it evolves over time. And there are four effects that are typically modeled. And the first one is the randomness in the number of offspring of a given individual or pair has in a given generation. And then there's mutation from one type to another, which is, we're all sort of familiar with that idea, that there's some concept of fitness, so that differences in the fitness among different types will produce different probabilities of having offspring in the next generation. And that it's possible to talk about migration in and out of an environment, but I won't really talk at all about migration. So the most, I guess, standard model in this field is the so-called Wright-Fisher model. So Wright and Fisher, they were statisticians in the beginning of the 20th century who kind of laid the foundations of population genetics. And Fisher, of course, has laid the foundations of large parts of statistics more generally. So what they assume is that there's a fixed population size, which we'll call large N, and there are only two types. So there's the ancestral type, which we call capital A, and the derived type, or the mutated type, which we call little a. So these are called the alleles. So there are two alleles. And so in the simplest case, the two types have the same fitness, and there's no mutation, and the sum of the number of little a's and the number of big A's is always going to be fixed at N. So what we do is we keep track just of the number of little a's from generation to generation. And in this model, t is really a discrete parameter. And it's just a Markov chain. So what we need to specify is the conditional probability that we're going to get j of type A in time t plus 1 if we had I at time t. So the standard Wright-Fisher model is the assumption that mating is random. So mating is, there's no real mating because there's no real there's no sexes in this model, so this is all kind of just illustrative language that doesn't really have any biological meaning. But okay, so how do you go from generation at time t to the generation at time t plus 1? Is that you just select them out of an urn. So this is what's meant by random mating. So you have an urn, and the urn has white balls and black balls, let's say, and the proportion of white and black is determined by the population at our current time, and then we just take out n balls. So it's an urn model with replacement. So it doesn't change the proportions within that urn to take out balls. So you can think of it having infinitely many balls of each type. Okay, so that means that the probability is just given by this binomial expression. Okay, now if you want to have migration and selection, what you do is you just twiddle the odds. I'm sorry, if you want to have mutation and selection, you twiddle the odds. So little a and big A have relative fitnesses 1 plus s to 1, and the rate at which little a goes to big A is mu1, and the rate at which big A goes to little a is mu2. Then what we do is we just change the probability. So you see here, there's a certain probability I over n, 1 minus I over n. Here, we just change those probabilities. So we have the same binomial looking formula, but we've changed what the probability of going from type little a to type big A and vice versa are, given by this formula that incorporates the rates of mutation up there and then the rates of selection there and there. So it's a very simple model, and there are many generalizations. You can have more types, you can have multiple populations with migration, but mostly we'll just focus on this simple case. Because actually in applications, the simple case is the case that's used most frequently anyway. Okay, so now the main topic of the talk concerns the operators, the differential operators that arise as limits of these sorts of processes as the population tends to infinity. So what you do is you rescale the population, so you just get frequencies instead of population numbers. So you divide by the number of individuals. And then you have to rescale the time. So you use as your time t times n. Now t is a real number, at least in the limit as n goes to infinity. And you get a continuous time stochastic process, which is parameterized by an interval 0, 1. And these things are typically described by differential operators, so Fokker-Planck equation. So in this case, the so-called backward Kolmogorov operator is the second order differential operator given by this expression here, x over 1 minus x, x times 1 minus x over 2 dx squared, plus then a vector field which vanishes at the endpoints, plus a vector field which is inward pointing at the endpoints. The vector field that vanishes at the endpoint, you can see that the coefficient is n times s, where s was the selective difference between the two types. And the coefficients of the non-vanishing part are determined by the mutation rates. So now, what we say when we take this limit is we assume that these numbers n mu1, n mu2, ns are fixed as n goes to infinity. And of course, biologically, that makes no sense at all because mutation rates don't change with the population size, and neither does the selective advantage. So it's a construct in order to get a limit. In actual practice, what you do is you say, well, I'm going to determine these numbers in my model by knowing more or less what the population size is and knowing what the actual mutation rates are. And that actually gives me coefficients in the model. So this statement that those are fixed as n goes to infinity, that's just to get a limit. When you actually use the model, you have to figure out how to compute those numbers to get approximate results for your actual discrete system. Okay. The forward operator is, of course, the formal adjoint. It looks like the same kind of a PDE, but in fact, it will satisfy different types of boundary conditions. So I call this class of operators Kimura diffusion operators, mostly because there probably weren't really, Kimura didn't write them down first, probably Wright-Fisher did, but Kimura used them first to really prove interesting things in population genetics. So I think it's pretty appropriate. Okay, so now, the fundamental solutions of these operators, so the solution to the equation dt p sub t is Lx on the one hand, p sub t, and of course that should be a y, or Ly, so it acting on the L transpose y acting in the transpose variable, and with the property that the limit as time goes to 0 is just the delta function. So this is the transition function for the continuous time stochastic process. So for example, if you start out with the allele at time 0 at frequency y, and you want to know what's the probability that the frequency is going to be in an interval between a and b at time t, you just integrate this p sub t in the x variable, and that gives you the probability. So you see how this sort of defines the continuous time stochastic process. Now, I'm going to have a little excursion here because I can't help myself. The Kimura operator is a remarkable operator. It sort of is the canonical differential operator defined on simplices. So simplices for us, in n dimensions, the simplex will be, you take non-negative coordinates that all sum to 1, and that gives you a simplex sitting in the positive orthant. The Kimura operator then has this formula, the second order part has this very simple formula. So it's xi delta ij minus xj, and then the second partial derivative dxi dxj. And that formula is the correct formula for any dimension simplex n. You get the same formula. It's like, this operator is very much like the Laplace operator. It doesn't matter what dimension you're working in, the formula is always exactly the same. This operator also has a very remarkable property with respect to the boundaries of the simplex. So the simplex is not a manifold with boundary, it's a manifold with corners. And it has this very complicated stratified boundary structure. And you get the boundary components by taking a collection of the coordinates and setting them equal to 0. And that gives you the components of the boundary. And there are many, many, many of them. A high dimensional simplex has a very complicated boundary. The amazing thing about this operator is that it is tangent to every component of the boundary, of every dimension. And what I mean by that is, if I take a function on some component of the boundary, so in the two-dimensional case, I just have a triangle. And if I take a function here, I extend it to the simplex in any way that I like. I let the Kimura operator in 2 dimensions act on it, and then I restrict it back to the boundary component. It didn't matter how I extended it. So in this sense, the operator is tangent to every component of the boundary. So it is a truly remarkable kind of canonical object. And has many, many interesting properties. I won't talk about that today, but if you're interested in this, I wrote a paper with Jon Wilkening on the eigenfunctions of this operator, and it has this beautiful, also stratified structure where you kind of build them from the stratification upward. So it's one of these complicated things. The eigenfunctions are all polynomials, but then you have to ask yourself, how do you order polynomials in many variables? It's a very non-trivial question, how you should order polynomials in many variables. And the simplex, the fact that you get these eigenfunctions sort of being built up from the stratification of the boundary gives you a very interesting way to order the polynomials in any degree, actually. Anyway, so if you're interested in that, that's an interesting paper. Okay, so the second order term, which is sort of the diffusion term, x1 minus x over 2 dx squared, it's related to randomness in the number of offspring. And strangely, at least if you're sort of just a casual observer of population genetics, mutation and selection in this model are actually deterministic forces because they're described by a vector field. So if the whole model were given by just that, if the diffusion term were 0, then it would be a deterministic model. There would be no randomness in the model. So this is just sort of we're not saying that mutation or selection are deterministic forces, but relative to the diffusion, they act like deterministic forces. Okay, now what makes it hard to study this operator is that the coefficient of the second order term, x1 minus x, vanishes at the boundaries. So it's a degenerate PDE. Now the paths of the associated SDE, the stochastic differential equation, are given by that Ito equation, this differential Ito equation. dx is square root of 2x1 minus x dw, where dw is a white noise process, plus b of x dt, that's a drift term. So the linear vanishing of the coefficient implies that if b of 0 is 0 or b of 1 is 0, then a path will reach 0 or 1 in finite time for this process with probability 1. So in fact, if both coefficients are 0, then with probability 1, every path will reach either 0 or 1 in finite time, and when it gets there, it stays there. So if the coefficients are non-zero, they're pointing inward. So we make a restriction on the signs. B of 0 is greater than 0. B of 1 is less than 0. So if you have non-zero mutation in selection, then what happens is you still can reach the boundary in finite time, provided the b's are small enough. But then you immediately go back into the interval. So you never leave the interval. So this is a process that allows paths to wander in the interval, reach the boundary, but always go back inside, unless the coefficient at that boundary point is 0. Okay, so the basic application of the forward equation is to understand how distributions of variance in an ensemble of population evolve over time. So that is, you take a bunch of different sort of replicates of the population that start out with different proportions of the little a and big A, and then you see how that sort of defines a probability measure at time 0, and then you see how that evolves over time. So the forward equation actually will act on Borel measures. But sort of this is a complicated context in which to do diffusion. And in fact, the semigroup which it defines is only strongly continuous on absolutely continuous measures. So you only get a good pointwise limit as time goes to 0 if you assume basically that your measure is an L1 function, so h of x times dx. And it turns out that if b of 0 or b of 1 is 1, you're allowed to add a delta function measure at 0 or 1, because they are absorbing states. That is, when you reach that point, you stay at that point. Okay, so if you're given an initial h of x dx, the solution then describes how the mass of this measure redistributes with time. If alpha and beta are not 0, that is, if both mutation terms are non-zero, then there's a unique stationary measure. It solves just L transpose W, stationary is 0. And what happens is that all solutions will converge to this measure as time goes to infinity. Now, again, it doesn't mean that any particular population converges to that distribution. It means that your ensemble of populations, if you look at how it behaves with time, it will converge to that measure. It's not a statement about any one population. It's a statement about a large ensemble of populations. Okay, if one or other of alpha or beta vanish, then the null space of L transpose consists of the delta function located at that point. So delta of x if alpha is 0, and delta of 1 minus x if beta is 0. If both of these vanish, then the delta measures are actually in the null space of L transpose. And these are absorbing states. Okay, now that's sort of the simplest description of what you might use this for, but it's really not used for that. It's really used for something a little bit different. So it's used to study something called the allele frequency spectrum. Now, the reason that I'll tell you what this is in a minute, and it's something which is actually difficult to understand the first few hundred times you see it. But the reason that it's very interesting is that if you have a population of organisms and you sequence their chromosomes, this is something you can actually measure. This is an observable property of a population of organisms. So, what you imagine is this. You suppose you've sequenced N chromosomes from a much larger population. And within those N chromosomes, what you've found are there K sites where there's some variation, where there's more than one type. Now, we make a very simple assumption. We assume that a site can either be unmutated, so there's no variation, or there's just two types at that site. And that's part of why we get to use the Wright-Fisher model to study it. This is what's called the infinite sites model. So further mutation and back mutation are assumed to never occur. So that is, you have infinitely many sites, and with some probability you'll get a mutation at a site, but the probability of getting two mutations at a site is 0. So the allele frequency spectrum is a sequence of numbers, F1 through Fn minus 1. Remember, there were N chromosomes. Fj is the number of sites where an allele appears in J samples. So these numbers are between 1 and K and are often represented as frequencies. So in the large N limit, remarkably, these frequencies satisfy a Kimura diffusion equation. Now, their statistics are affected by changes in the population size, by changes in mutation rate selection. So this is really an interesting way to try to understand something about the history of a population, is to try to look at the allele frequency spectrum, and then you build models for what you think might have produced this population, and then you try to figure out what parameters in those models give the best explanation for the observed data. So this is something that's actually done. So here's, for example, an example of an allele frequency spectrum. So you have 8 SNPs, 8 places where you had polymorphisms, and you have 6 samples. So you count the number of occurrences of the SNP in your population, and then the spectrum is just these numbers, this sequence of numbers. Now, one should be aware that, again, in this idea, we have this infinite number of organisms lying in the background that we're not really looking at all of them. We're just looking at some of them. So the largest segment of our population is the segment where zero mutations have occurred. And that's sort of an infinite size set. So you expect actually more mutations occurring once. Okay, so many problems in population genetics are addressed using these kind of diffusion models. So Kimura and Crow were the first people, and then Ota, and then Warren Ewens. So more recently, Nick Patterson, Evans, Steve Evans, Schvetz, Slatkin. So they've used these for all kinds of real biological problems. And mostly what they've done, certainly Crow and Kimura, mostly what they would do is they would find instances where they could write down the answer. That is, they could write down a formula for the solution to the equation. And then they would use that to say things of a biological nature. And then at some point what happened was people sort of ran out of examples where they could write down the answer. And then they sort of thought, well, we'll try to do numerical things. But now remember, this equation is an equation where the coefficients of the leading order term vanish, which means that the boundary conditions that you can specify at 0 and 1 are not standard Dirichlet and Neumann boundary conditions. They're not pointwise boundary conditions. There's things that are more complicated to describe. There are things that are, I would say, for all intents and purposes, impossible to enforce using finite difference approximations. So, but of course, historically, what people have done is they've attempted to solve these PDEs using finite difference approximations. And much to their horror, they would, often get probabilities that were negative. So they realized that there was some serious problem with solving these equations numerically, but they didn't really know how to address this problem. So what happened, I think, partly was that this forward model was sort of abandoned. And it was replaced by something called the coalescent, which is a different probabilistic description of populations where you build genealogies. You try to understand sort of you see a bunch of genomes now. How did they start out at some root, and then through a process of successive mutations and divisions, how do you end up with what you see today? And most of population genetics today is really done using this coalescent model. But I really think it's because nobody could solve the equations accurately. It's not because they weren't useful. It's just that no one knew how to solve them. So a long time ago, I started studying this question, and it's one of these interesting things where you see a model, which is clearly a very sort of central model in an empirical science field, and you're astonished to learn that 75 years after the model was introduced, virtually nothing is known about it. There's no mathematical analysis to speak of this model. So I spent some years working on this. So the one-dimensional case had been studied to some extent in a very classic paper written by Feller in 1952. And what he asked himself the question, suppose I have a differential operator like this one, even a little bit more generally. And he said, what are all the ways that I can define a closed operator on a Banach space with this formal symbol so that closed operator generates a positivity-preserving semigroup? And then he also asked this question about what about the adjoint semigroup? What does it look like? And is it generated by the adjoint operator? So he completely solved this problem for this class of operators. A very remarkable paper. Okay, so we're going through this whole theory. He found a huge selection of operators and very many kind of remarkable different processes. Many stochastic processes can be defined by this. Largely, what makes these processes, where they come from, is he allows that a path can leave the domain at a boundary point, 0 or 1, and then it reappears at some point in the interior with some probability. And this is sort of how you get a lot of different semigroups out of this one model. Anyway, we're not going to study anything so complicated. So the simplest choice for functional analysis of such an operator is you take what's called the graph closure, which I call L bar. And what you do is you just say, okay, let's let L act on twice continuously differentiable functions in the closed interval. And we're going to just look at the norm of the function plus the norm of L of the function. And we take the closure of C2 in that topology. And that gives an operator which is called the graph closure. And that turns out to be defines a strongly continuous positivity preserving semigroup. And it's one actually that's sort of the most useful one in applications. Now, the domain of the operator is described by regularity conditions at the boundary points. And the precise nature of these conditions depends upon the coefficients alpha and beta, whether the vector fields at 0 and 1 are actually inward pointing or they vanish. In all cases, what happens is dx squared is defined in the interior, but typically you wouldn't expect it to be defined at the boundary. But what's defined is the limit of x1 minus x dx squared. At each point, it has a limit, and it's 0 at both boundary points. If alpha or beta is positive, then a function belongs to the domain, provided that the first derivative itself has a limit at the boundary point where the coefficient of the vector field is positive. The solution to the diffusion equation with these boundary conditions is what we call the regular solution. And it's uniquely determined by its initial data and these regularity conditions. So that's a little strange because I haven't specified the boundary behavior other than to say that I'm looking for a solution that has a certain degree of regularity at the boundary. But that does actually uniquely specify the solution. In population genetics, this is sometimes called the no-flux condition because there's a way to describe this in terms of limits of derivatives that look like sort of Neumann conditions, but they are scaled by x to n1 minus x to powers. But this is a little bit easier to understand. Okay, so the key thing here is to realize that the solution is determined by its regularity at the boundary. And this indicates why it's not possible to accurately solve these problems using finite differences, because with finite differences, it's very difficult to tell what the regularity of the solution at the boundary is, because you just have a discrete set of points. You don't really know. Okay, now For the regular solution, we cannot specify either Dirichlet or Neumann data at the boundary. Unlike the case of a non-degenerate operator, regularity alone implies uniqueness. The regular solution has the following rather remarkable property, which is that if I start out with data which is in Cm, in the closed interval, then the regular solution is in Cm of 0, 1 cross time down to time 0. So I get uniform Cm regularity down to time 0 if my initial data is in Cm. And then, of course, it's smooth for positive times. It's C infinity up to the boundary for positive times. Okay, and the conditions that you specify at the two endpoints are largely independent of one another. Now, it turns out that if the strength of the mutation is weak enough, that is, if alpha is less than 1 or beta is less than 1, then you can define a closed semigroup where you have homogeneous Dirichlet boundary conditions. That is, I can insist that the solution go to 0 at one of those endpoints or both of those endpoints. And the solution satisfying this condition, however, necessarily has a singularity at the boundary. So if alpha is between 0 and 1, and I want the solution to be 0 at x equals 0, then the solution is going to look like x to the 1 minus alpha at that point. And similarly, if I want it to be 0 at the 1 boundary point, then it's going to look like 1 minus x to the 1 minus beta. If alpha and beta are greater than or equal to 1, then you can't specify Dirichlet boundary conditions. And interestingly, sort of this is a reflection of something about the stochastic process. If alpha and beta are greater than or equal to 1, then the paths of the process never reach the boundary in finite time with probability 1. So it's only if the strength of this vector field is weak enough that the paths can even reach the boundary. If the paths can reach the boundary, then you can specify data there. If the paths can't reach the boundary, then you can't. Okay. So now when alpha is 0, which is actually a very important special case, we get an x log x singularity or a 1 minus x log 1 minus x singularity. Now, suppose we would like to impose inhomogeneous Dirichlet conditions. Well, what we do is we want u to be h0 at x equal to 0, and we want u to be h1 of t at x equal to 1. So then what we do is we write the solution in that form, 1 minus xh of t plus xh h1 plus u0, where u0 is now a solution of an inhomogeneous diffusion equation. So there's a right-hand side in the PDE, but it has homogeneous Dirichlet condition. Now, what this means, again, is that u is not going to be smooth at the boundary. You're going to have singularities at the boundary. If you want to specify the boundary behavior, you have to pay the price. Okay, now the work that motivated, the paper that motivated our numerical work was this paper by Evan Schvetz and Slatkin. And they were studying Kimura diffusion to estimate quantities connected to the allele frequency spectrum, but with a varying population. I'll tell you why in a second. They're looking for a solution to this problem. dtu is 1 over 2 rho of t, where rho is now going to be the population, times the diffusion term. Plus here we just have a selection term, and there's no vector field. There's no inward pointing vector field. So you can specify Dirichlet data. And the initial condition is some u naught, which comes from some stationary distribution of some other process. And the left boundary condition is that you want theta times rho of t, where rho of t here is this population size. And the right boundary condition is that you want u of x and t at 1 to be 0. Now, this came from some research that people were doing when they were trying to understand what proportion of the human genome comes from Neanderthals. And it all had to do with sort of estimating population models. How did the population of these two groups change over time? And they needed to solve this problem. And Evans, I saw Evans give a lecture about this, and he said, I couldn't solve the PDE satisfactorily, and so what I did was I simulated the stochastic process. That's myself, boy, that's insane. And I said, what are you kidding me? You couldn't solve the PDE? And he said, no, we just could never get accurate enough solutions, so that we had nothing that we could do but solve the PDE. Stimulate the process, which, this is something that takes just tremendous amount of time because it converges incredibly slowly, these simulations of stochastic processes. So for the allele frequency spectrum application, this function u, which we're going to solve for, isn't quite the allele frequency spectrum. You actually have to divide by x times 1 minus x. And this is a reflection of this fact I was saying, that the most likely thing is that there are no mutants. So that's why you get this denominator that blows up. the numerator doesn't at x equal to 0. At x equal to 1, you get a finite limit because you force the solution to be 0 there also. So in the end, you'll actually get a finite limit. Theta, this thing that appears here in the boundary condition, is actually related to what's called the per site mutation rate, the probability that any given site will experience a mutation. Okay, so this is a very challenging problem, and the problem is challenging mostly because you're imposing this Dirichlet condition that forces the solution to be singular. And it's not just that it's singular at time 0. You're inserting a new singularity at every successive time. So you have to really resolve this singularity. Okay, so let's talk a little bit about the asymptotic behavior. So we sort of use these operators, L alpha beta. So it's x1 minus x dx squared plus this linear vector field, which comes from the mutation term. These are sort of our reference operators. And in fact, the domain of the operator, sort of in the functional analytic sense, is determined completely by alpha and beta. So these are sort of, everything is a perturbation of these operators. Okay, so it's useful to consider how the asymptotic behavior of the regular solution depends on alpha and beta. So if you take the operator L00 plus a selection term, there's a two-dimensional null space spanned by 1 and some function, V0, where V0 of 0 is 0, and the derivative of V0 is positive for all x, and a regular solution to the equation with initial data 0 at the boundary points. And therefore, u of x and t will converge to some combination of these two things, where a is just u at 0, and a plus b v of 0 is u0 of 1. So if alpha and beta are non-zero, then the operator has a null space spanned by constant functions. The PDE can be rewritten in this sort of divergence form, where w is this measure, x alpha to the 1, alpha minus 1, 1 minus x to the beta minus 1, e to the s of x, where s of x is just the indefinite integral of the little s of x, which is the selection coefficient. And hence, the limiting value is equal to that, because this is a conserved quantity. Well, similar considerations apply if one of alpha or beta is positive. Okay, so now what about numerical methods? Many years, people solved the Kimura diffusion equation using polynomial eigenfunction expansions. Because you look at this operator and you observe this very interesting thing about it. Because the coefficient of the second derivative is a polynomial of degree 2, and the coefficients of the first derivatives are polynomials of degree 1, this operator maps polynomials of degree d into polynomials of degree d for every d. That means that it has a basis of eigenfunctions that are polynomials. And in fact, the basis of eigenfunctions are classical polynomials. They're what are called Jacobi polynomials. So L alpha beta of Pn alpha beta is minus n alpha plus beta plus n minus 1 times p alpha beta. And p alpha beta is just a rescaled version of the alpha minus 1 beta minus 1 Jacobi polynomial. The Jacobi polynomials are the polynomials which are orthogonal with respect to that weight where that's not there, just that x to the alpha minus 1, 1 minus x to the beta minus 1. That's how you get Jacobi polynomials. Okay, and you can also figure out exactly what the eigenfunctions are when alpha and beta vanish by taking limits if you're careful. Now, the solution will be given by a standard sort of infinite sum formula. So you have fj, where fj's are determined by the initial data, and then you have these e to the t lambda j alpha beta, pj alpha beta, and these lambda j alpha betas are back here. They're quadratic in n, or j. I guess I've switched from j to n. So they're quadratic in j. So it's like e to the minus tj squared that converges very, very fast as soon as t is a little bit positive. So, of course, I told you that these solutions become very smooth at positive times. Okay, so finite partial sums do in fact give spectrally accurate approximations to the solution. But here's the thing. You have to calculate them very carefully. And this is a thing that, of course, applied mathematicians know, and most people who aren't applied mathematicians don't know. Even pure mathematicians tend not to know this fact, that evaluating polynomials of high degree, and I mean high degree could be 20, is extremely difficult to do accurately if you're not careful about it. Now, these polynomials, coming from basically applying the Graham-Schmidt process to monomials 1x, x squared with that weighted measure, they satisfy a three-term recurrence relation, which I write out here, where these coefficients bn plus 1, an, and bn, these are all explicitly computable quantities, not hard to compute. In fact, can be found in any number of standard books. And this gives a stable way to compute the polynomials. If you try to compute the polynomials in terms of their expansions with monomials, you very accurately get results that are completely meaningless, almost no matter how many digits you try to keep track of. So this, I think, was a problem for population geneticists, that they thought, well, even the eigenfunction methods don't work. And the reason was they didn't know how to compute the eigenfunctions. They tried to use the monomials. They thought, oh, we'll be very clever. We'll use Horner's method, which is some slightly improved method for computing polynomials. But in the end, it's catastrophic. And the problem is just simply this. So these are the coefficients of the polynomials in terms of the monomial basis, the CNKs here. And you see that by the time n is 30, you get coefficients that are around 10 to the 16th. And what happens is these coefficients are gigantic, and they alternate in sign. And of course, you're evaluating these polynomials at numbers between 0 and 1. So what you're doing is you're taking sums of enormous numbers of alternating signs, and you're hoping to get a number that's like around 1. It doesn't happen. This is what's known as catastrophic cancellation. So Jon, being Jon, worked this out for the case n equals to 23, where alpha was 1/4 and beta was 3/4. And what he did was he computed the polynomial using the recurrence. That's the black line. Of course, it's perfectly accurate, like it's accurate to as many digits as you like. But over here, you see when you get close to the right endpoint, even for n equals to 23, using the monomials, you got no digits. That was the size of the error. And here was using Horner's method. That was the size of the error. So the problem is, unless you use three-term recurrence relations to compute the polynomials, you cannot use them to represent your functions because you just simply can't get any digits out. Okay, so the eigenfunction approach is only directly applicable to the case where L is equal to this operator L alpha beta, because that's the case in which you can actually write down the eigenfunctions. And if you're interested in solving the more general equations, which we are interested in, and in fact, we're interested in solving an equation where alpha and beta are 0, but we do have a selection term, and also we will have a non-homogeneous term, we need another method. So it's important to solve inhomogeneous problems because we're led to those very quickly if we try to solve problems with inhomogeneous Dirichlet conditions, as in the allele frequency example that we had above. So this term, x1 minus x, s of x, d by dx, the selection term, is in every sense a lower order perturbation, so that it's a relatively compact operator. The domain of the operator is totally insensitive to adding that term or not having that term. So it's really a perturbation term. Okay, so we're going to talk about two other methods. So the first method employs orthogonal polynomials, which are defined by this weight function here, where we include the selection term in the weight function. So s prime is little s. So capital S is just the indefinite integral of little s. Now, if s is not 0, the functions we get by applying Gram-Schmidt with this weight are not eigenfunctions. But if you choose the points carefully, you get a discretization that actually leads to an exact Galerkin approximation. So that is, you have a basis of functions, and what you do is you write your equation in some weak form in terms of that basis of functions, and you restrict yourself to a finite dimensional subspace. And then the exact Galerkin approximation is the best solution you can find in that finite dimensional subspace. And by using this weight and these polynomials, you can actually get an exact Galerkin approximation, but without actually using the weak formulation. So we call this the Galerkin pseudospectral method. It's described in great detail in our paper, and I won't consider it further. I'll just show you an example where it was used. But once again, it's very important to use three-term recurrences to evaluate these polynomials. Now, the second approach, which is an approach, of course, we like a lot better, is an approach where we replace the PDE with an integral equation. So the integral equation is known as Duhamel's formula, or the variation of constants formula. So we assume, we write U as here's sort of the unperturbed e to the t L alpha beta term. applied to the initial data. And then we integrate from 0 to the current time, this sort of correction term, which gives us the lower order correction terms and the inhomogeneity. And where in our instance, e to the t alpha L alpha beta will be the regular solution operator for the reference equation. Now, starting with this formula, one is discretizing the solution operator for the PDE. We like to emphasize the integral equation involves the solution operator, right? Because what appears here is the heat kernel, which is the solution operator, and then some average of heat kernels over a history. So when you discretize the solution operator for PDE rather than the PDE, it's inherently well conditioned. Whereas the definite difference or the Galerkin approximations, when you decrease the mesh size or increase the order, you're increasing the condition number of the linear system, so it's inherently ill-conditioned. It gets worse and worse conditioned the more digits you try to get, the less digits it's willing to give you. So it's always better, if you can do it, to find an integral equation formulation and discretize that. I should also go back here to say, in this method using polynomial expansions, you're imposing the boundary condition very, very adequately, because you know these coefficients here go to 0 very fast, and so you get solutions that are very smooth up to the boundary. So you are actually getting the regular solution. And as I say, it's a spectrally accurate approximation to the regular solution. Okay. So the main challenge is to find a way to approximate the kernel of the heat kernel, the e to the t L alpha beta. So the heat kernel for the reference problem. Now, a simple approach is you just use the eigenfunctions. You can write it like that, where the phi alpha betas are appropriately normalized eigenfunctions. And in principle, it's a rapidly convergent series. But the problem is this. To time step this problem, to go from one time to the next time, you see here that we have this t minus s. And for the important part of the solution, t minus s is actually going to be very small. So you're not getting a lot of rapid convergence here because you're going to be evaluating this t at very small values. So while in principle, it's a good idea, in practice, it's actually hard to do it carefully enough. Okay, so what we do, and now I'm going to delve into some very technical sort of looking numerical analysis, which I have to admit again is almost entirely the work of my co-author, Jon Wilkening. So what you do here is you split the time interval into, so you have some fixed h, which is your time step. You fix that interval into subintervals, and these subintervals are going to be multiples c sub r times h of the time step, and these c sub r are what are called Gauss-Lobato quadrature nodes. Now, because everything is being done doing integration, basically we have to do everything by picking good nodes for doing numerical integration, or quadrature nodes. So given a u naught, we seek functions u1 through u nu, such that if we use a polynomial interpolation in time to define the action of the perturbation term on these functions for s in that interval, then the resulting solution will actually give u of x at these times will be these vectors that we find. So what is this equivalent to? Well, you should write out the whole thing as a linear system. So u sub r, that is the solution that we seek at time t sub r, is the background heat kernel, ECRH L alpha beta applied to the data, initial data, plus a sum over the history evaluated at each of these points, at these points C sub r h, where ARJ of HA, well, that is this exponential integral. So it's the heat kernel applied to the basis of interpolating polynomials. Okay, so this is how you find a linear system that you want to solve. But then you have to figure out how to compute these coefficients here, the ARJ of HA. So we rewrite the system of equations in this form, and it's a pretty nice looking system. We write it as I minus H matrix A times matrix B equal to some vector on the right, F. And actually, you can very easily estimate the norm of AB. It's going to be some constant times the Lebesgue number of the nodes. So the Lebesgue number of the nodes has to do with how bad a job you do when you use these interpolating points to evaluate a function away from the interpolating points. So with the Lebesgue number, as you do the following, you take a function, you interpolated through those nodes, and then you look at the sup norm of that function at other points where it isn't interpolated. And this is where you can really win or lose in this game. If you, for example, pick uniformly spaced sample points, then that number is going to grow exponentially in the number of interpolating points. If you pick cleverly selected sample points like Gauss-Lobato points or Chebyshev points, then the number grows logarithmically in the degree. So that's why one of the reasons we use these Gauss-Lobato nodes. With Gauss-Lobato nodes, this so-called Lebesgue number grows like the logarithm of the degree times 2 over pi. So you see here that matrix is multiplied by this small number h. So at least on the face of it, it looks like a perfectly nice, well-conditioned system of equations. Okay, so we need methods to evaluate these aij of HA. So these functions evaluated on the operator. And the problem is that there's this so-called stiffness problem, that the eigenvalues go very rapidly from being around 1 to being very small. And you have to avoid kind of numerical artifacts that tend to arise when this happens. And the simplest case, which we do in part 1, we just assume the operator can be diagonalized. So for example, if it's L alpha beta, and then what we need to do is we need to evaluate certain scalar functions. We call them gamma n of lambda, which are exponential moments of Chebyshev polynomials. It takes a few steps to get there. It's not obvious that that's the right thing to do, but that's what we do. So then what we need to do actually is we have the eigenvalues, we have a matrix which is basically constructed out of samples of the eigenfunctions, and then what we need to evaluate are these functions of our operator at the point CRH, and they're just then obtained by a diagonal matrix, which is just these scalar functions, gamma m of lambda, evaluated at the eigenvalues multiplied by CRH, and then just conjugated by the basis of eigenvectors. Okay, so we do some examples with this method. So we're solving the heat equation with alpha equal to 0.2 and beta equal to 0.7. And then we have this selection term, minus 5x times x minus 1. And the initial data is the sine squared of pi x. So it goes from 0 to 0, but through this hump here. And we evaluate this using our method. And we evaluate this using the Galerkin method. And what we see is that these two methods give results that are within basically 10 to the minus 15 of one another. So it's not a proof that they're correct. It's just a proof that they're the same. Okay, then we had another example where we allowed the population to vary with time. So we did two examples where the population is fixed at a half, and an example where the population is 1 plus t over 2. And here, you see this, so the population now appears there in the denominator of the diffusion term. And the interesting thing here is Jon plotted the sizes of the polynomial mode amplitude. So here we're in a case where we're using the eigenfunctions of the reference operator L.2, 0.7, and so the eigenfunctions are just Jacobi polynomials. And here, what he did was he plotted how the coefficients depended upon the time and the degree of the polynomial. And you can see by the time the degree was about 25, the coefficients were down around 10 to the minus 16 in all cases. And they just stayed small like that. So sort of demonstrating the spectral accuracy of this method. All right, now, okay. So we wanted to do this application to the Kimura to study the behavior of the allele frequency spectrum in this very unpleasant problem where we're going to inject data at one of the boundary components. So we have a singular solution. So this is the problem we want to solve. The equation is very simple. It's dtu is x1 minus x over rho dx squared u. U of 0 in t is fixed to be this theta times rho of t. U of 1 of t is fixed to be 0. And the initial condition is just that u of x and 0 is theta times 1 minus x. Okay. Now, for the population model of interest, rho of t is kind of imagined to be 1 for all negative times. And this is sort of where the initial data comes from. What you imagine is the population was fixed up to some fixed time. And what has happened is you've reached the stationary distribution, which is this theta times 1 minus x. Then the population starts to grow exponentially. So rho of t becomes e to the RT. And R in this case is 40. So it's growing pretty fast. And the solution to this equation, of course, is singular along the x equal to 0 boundary, with a leading singularity of the form a of t times x log x. So the methods we introduced earlier that compute e to the t minus s L00 using the eigenfunction expansions are not adequate to resolve the singularity at x equal to 0. And so we introduced a different method. And what we're going to do is we're going to represent the exponential e to the t minus s L00 as a function of the resolvent of the operator. So identity minus h L00 inverse. So note that the resolvent is the Laplace transform of the heat kernel. So if I take e to the minus t L00, or e to the t, I guess L was, that negative sign is wrong because L00 is a negative operator. So if I take the Laplace transform, which I have right here in equation 29, I see what I get is 1 over L00 minus lambda. Well, I mean, that's just a formal calculation, but that's actually true. I do get the resolvent kernel if I take the Laplace transform of the heat kernel. Now, one of the things I'm best known for is my paper showing that you cannot invert the Laplace transform, generally speaking. Nonetheless, Jon found a way to represent the heat kernel as a function of the Laplace transform. And this is a surprising thing to do, and it's a surprising thing that it's a good idea to do it. But it is. Now, the resolvent kernel can be expressed in terms of Gauss hypergeometric functions. So these are all, I don't know how many of you are devotees of Gauss hypergeometric functions, but they're remarkable classical functions. They have a nice series expansion like that. They have a nice integral expansion like that. You have to make some hypothesis about the A's, the B's, and the C's in that expansion, but that's how it is. Now, to use this representation of the resolvent used for the exponential, once we've done this, the reason we do this is that we can introduce adaptive coordinates near to x equal to 0. That is, we can rescale near x equal to 0. And I'm going to show you a plot, and you're going to get some idea about how extremely radical Jon was about rescaling and how many digits he was trying to get. Now, to give you some idea what the problems were here, in order to resolve what he wanted to resolve, he had to pick h so small that the dynamic range of the of the hypergeometric functions that go into the computation of the resolvent is 1 to 10 to the 13,000. I kid you not. And you might wonder how you can ever represent anything that has dynamic range 1 to 10 to the 13,000, or maybe you'd wonder why you'd want to do it, but he did. So Jon was undaunted by this because he wanted to compute solutions to the problems out to time 0.3. And remember, we have this e to the 40t is our population at time t. So at our row of 0.3, you had 162,754. So it's a lot larger than you started out at time 0 where you had 1/2. Okay, so I don't have time to explain how to do this, and I'm not sure I could even if I did. But hopefully this software will soon be available online so you can use it without understanding how it works, which I would recommend. But here are some examples. Okay, so in these plots, time is ordered from red to yellow to green to blue. So this side, the blue edges here, those are the last times that we computed for. Time is 0.3. And the early times are down here. Now, if you look at the scale of this plot, you'll see it goes from 10 to the minus 25 to 100,000 on the y-axis, similarly there. And what we're looking at here is the difference between our solution and the initial data. So that's why the red curves, which are the early curves, are way down here in the 10 to the minus 25 zone. And what you see is that something sort of slowly is moving up and out to the right like that. Now, but it's very hard to see what's going on So John blew up the coordinates there. And you can see now the scale goes from 10 to the minus 10, 10 to the minus 8, 10 to the minus 6, 10 to the minus 2, and eventually to 1. And what you can see is that there is this boundary layer that is coming out of the corner and moving up and over so that, here, by the time you've gotten to, I can't really say what these times are, I'm afraid. But by the time you got to that blue curve there, at x is equal to 0.0001, the value of the solution is made it all the way up to 10 to the minus 5. And then a little later, it gets up to 1. And then eventually, as you see here, the solution does get up to 100,000. So this is the resolved picture of the evolution of that problem at a very, very, very refined scale. Okay, so I think I'll stop there, and thank you for your attention. Is that if people would like to solve these equations, these Kimura diffusion type equations, it's really now possible to do it. And you can now really solve almost as awful a problem as you can cook up and get as many digits as you want. And Jon Wilkening has done all of the hard work for you. And all you have to do is wait until he puts the software on GitHub, and then you can solve these problems too.
Other questions?
Yeah.
Could you add migration?
Yes, you can. I mean, so what you do is you just basically have two intervals, or you have a product, x and y, and then you have a term that sort of describes the transition from one population to the other. So you can. So you take the sum of the two of them and you add another term. So you have they'd be two independent diffusions, but then you have a term. I guess you take two one-dimensional diffusions and then you just have a term that describes motion from one population to the other. And people do this.
Maybe I was thinking like the solution depending on space continuously, so that you end up
want to
with
put in spatial variables. Well, I think the answer to that question is yes. So you could have a diffusion coefficient that depended upon spatial variables. You could put a population that depends on spatial variables. But again, what it's about. So it's about variance, like the distribution of variance in the population as a function of a spatial variable and a time variable. I guess you could do it. I have never tried to do it, but I suppose yes. I mean, because this just describes how the variance, how the variation in the composition of the population changes, and you could also have terms that describe the diffusion within space. I mean, I guess, there was a lot of work by David Nelson at Harvard. He's a statistical physicist who worked on these kinds of problems where he was studying things like the way bacteria. So you would have a plate with agar, and you'd stick some bacteria, and then they grow out in these sort of waves. And then what you'd have is mutations occurring, and then you'd have these sort of interference effects at the boundaries. And he could study how the boundaries between the different mutants would evolve spatially and in time. So there is work like that. I'm not exactly sure what he used as a model for that, but I know that even experimental work, which was then also discussed in a model. So if you look at this work of David Nelson in about 10 years ago,
okay,
or maybe a little bit more, they definitely did that kind of modeling. Yes.
Must be used to solve like generic form of Fokker-Planck equation.
Well, it depends what you want to do. I mean, the generic, it depends really, it depends on the coefficient of the second order term mostly. If the second order term is degenerate, then you have to use a method like we used. If the second order term isn't degenerate, then there are lots of ways to solve it. Even finite difference methods work pretty well. Not that I'd necessarily recommend them, but they do work pretty well. Yes, it depends yes, for all, I mean, certainly, I should say the Duhamel formula, right? This formula that we sort of start this discussion with this formula. This formula is really a very general prescription for solving a lot of different types of parabolic problems. And so it entails being able to compute this operator e to the t L alpha beta. So that you have some operator which you can actually pretty well compute the heat kernel of somehow or the other. And as long as you can do that, you can use this to solve the perturbed problem pretty effectively. But whether you have to do the kind of things that we did depends upon whether the operator has these kind of degeneracies or not.
Thanks.
So I would say, yes, generally speaking, this is a good way to solve Fokker-Planck equation. Yes.
You had that decomposition of the operator into like I minus HAB before, and you talked about the Lebesgue number growing logarithmically in the degree of your quadrature scheme.
Yes.
As I take my h to 0, how do I have to grow the degree of my quadrature scheme to maintain some level of error? Like, does this grow linearly? So this is like a nice decaying.
Well, the degree, so the degree in this approach determines the sort of accuracy in time, right? So you've taken a time interval from 0 to h, and then you've broken it up into subintervals, and that gives you some effective order in time. I'm not exactly sure what you're trying to do. If you make h smaller, yeah, I mean, you make h smaller, then it becomes harder and harder to compute this matrix, this A matrix, which requires exponentiating the operator. We didn't really think about the relationship. I think basically we're just saying we'll fix some reasonable order in time. Like, I think, knowing Johnny, probably something like 12th order in time. But h was quite small. I mean, that's why you ended up in this, because you see, again, in this approach, you're computing, you're representing, where'd it go? Anyway, you're representing the heat kernel in terms of the resolvent kernel and this operator here. When you take h smaller and smaller, it becomes closer and closer to being a delta function. That's really what's happening, is that it's becoming more and more and more peaked. And that's why the dynamic range is so enormous. So it's actually interesting because the dynamic range of the hypergeometric function is enormous. But in the resolvent kernel, you multiply two of them together always. And the dynamic range of the actual resolvent kernel is not that enormous. And it's just a question of accurately computing these two things so that when you multiply them, you get reasonable numbers. And what he actually does to do this is he replaces the hypergeometric equation with the Riccati equation, which is the equation satisfied by the logarithm of the hypergeometric function. Which is a nonlinear equation, but turns out to be a lot easier to solve. And of course, if the dynamic range of the hypergeometric function is 1 to 10 to the 13,000, the dynamic range of the logarithm is 1 to 13,000, or 0 to 13,000 is nothing. It's not a problem. So that's really what he does. Then, of course, you have to eventually exponentiate everything. And so that you use these tricks where you sort of divide things up into overlapping panels, and you never work with really big numbers because you always use the previous results to kind of build the next results. And everything is done as products of ratios of products, and nothing ever gets to be very large in the end. So you never actually compute the resolvent kernel at 10 to the 13,000.
So I don't work in population genetics, so this is all quite unintuitive to me. But I was curious, the boundary layer you showed, what does it actually correspond to in the original model? Is it that one allele is?
Well, what you're doing is you're injecting mutants. That's what that boundary condition really is. If we go back to what you're doing is, I go back to this Evans and Schvetz problem. Where'd it go? What you're doing is you're looking at this population where you know that yes, there it is. There, you know that what's happening is as time progresses, more and more and more mutations are arising. And they arise at a certain rate, which is just proportional to the population size. So that's why it's theta rho of t. So, and then you got to see sort of how they sort of filter down. And the idea is every mutant occurs someplace once. So every mutant appears in the first instance at one site. And then the question is, then how many sites do they sort of appear at as time goes by? So that particular type of mutant then could reproduce and produce lots and lots and lots of copies of itself, or it could go away. And that's sort of what the model is trying to tease out.
Gotcha.
So if you start out with one mutant at time-based, at some time, how does that filter then through the population? So that's what it's about. And then, but again, this is something that you can observe in a population. You can actually look at the chromosomes of a population of individuals, look at the places where you have mutation, count the frequencies. So it's an actually observable quantity that has a lot of information in it. And population geneticists really like this particular quantity, the allele frequency structure. And it has also this amazing property that its evolution is described by a one-dimensional heat flow. So it's hard to get something better than that from the perspective of mathematics.